So I'm Prajwal. I'm a postdoc at MIT. And today I'm going to be talking about spot coverages of exoplanetary host star using HST data. So this is a program led by Ben, who is sitting right over there. And this is a group effort. So without further ado, and you might be all excited about the networking event, so I don't want to take too much of the time. So I think this talk is slightly different than the talks we have been hearing here. So I'm going to be talking a little bit about some of the introduction. So the first thing is I want to explain what transit light source effect is. So when you are measuring the radius of the planet, we usually assume the star is uniform source of light. But if there are faculae and spots, the measured radius of the planet changes, and there is a color dependence. And when we are trying to study the atmosphere of the planet, one of the things that what happens is you get your transmission spectra is contaminated by this offset. So people who are working in transmission spectra, they are pretty much worried about what signal is actually coming from the star, what is actually coming from the planet. So it's a big problem. So what we are trying to do with this program is actually leveraging the spectra we already get during transmission spectra. So for transmission spectra, this is actual data for HAT-P11. You can see there is like a forward scan, reverse scan, and for people who have been seeing like the really great JWST data, this is probably a step down. But even for Hubble, like one of the things, once you start working with this data, you realize that how stable the instrument actually is. You go between you visit the same star, say within in a span of 5 months, and you can see the spectra actually, is pretty stable. When you take the medium spectra and look at the scatter it's almost impossible to see. And we are trying to use this data and feed for the SED, use the Phoenix model, use the information that we get from the Gaia, and get some information about the star itself. So I'm going to be talking about what our main goals are. So we want to do uniform reduction of HST data, and the ultimate goal of our program is actually to get some sort of idea about how spotted the star is and sort of understand how it changes across time, and also understand how is that information about the spottedness of the star going to impact our retrievals or the transmission spectra. So we are very fortunate to have like Gaia distance. Those things really help to constrain the temperature really well. And here are our 16 targets. So we had a lot of targets to choose from. We had to sub-select some of them. And we span the temperature range quite a lot. We go from AIM-8 TRAPPIST-1 to WASP-121 F3 star. And we have multiple people in the group. So David, who's not here today, but he is focusing on STIS. Rachel is focusing on TRAPPIST-1. People who have been seeing the spectrum for TRAPPIST-1 might know, this stellar contamination has been a big problem. And Isaac, who has done the pilot study with SD189. And I'll be talking about his study, which is the basis for all of our work. So the pilot study actually used G141 data. So we have been trying to expand this with all the different instruments with Hubble. So I would like you to give 3 guiding questions as I'll be talking about this our results. So the 3 guiding questions are how spotted the exoplanetary host stars are, and what is this the temperature and the spot covering fraction, and do they change over time, and how are they going to impact exoplanet atmospheric retrievals. So these are some of the really ambitious questions which we are trying to answer. So we don't have perfect answer to these questions yet. The result I'll be showing is a little bit preliminary, but it will sort of explain the direction we are heading. So first of all, I would like to show some of the spectrum we extracted for 16 of our targets. And this might be a little bit hard to see, but here we have data for G102 and for G141. So this is the flux on the surface of the star. So obviously the coolest star, TRAPPIST-1, is at the bottom, and the hottest star is at the top, WASP-121. So when I plotted, when I made this plot, like one of the things that sort of struck me is for WASP-121, the spectrum, sort of lines between G102 and G141 band. Whereas if you look at the AU-meek, you sort of see this vertical offset. So this is still we're still debating, we're thinking what might be causing this, and we're still trying to understand if there are some systematics within Hubble that might be causing this. But I'm on the camp that this offset that we see for AU-meek between G141 and 102 is because of the stellar activity. And another thing I think which was fairly interesting, and we don't have a perfect answer to this yet, is we sort of see the SED, they crisscross one another, so that might be indication of the stellar contamination, but we are not sure yet. We need to do all the analysis for all these targets before we can say anything perfectly. So one of the things we are doing simple SED fits, and we use the priors from the Gaia, the distance, and we are able to get the radius for the stars when we assume a single temperature component. So this is for assuming the whole photosphere has one temperature, and except for a few targets, the radius pretty much matches pretty well. And this target is actually AU-meek, and this one right here is HD189. I'll be talking about HD189, but AU-meek, as you know, has a lot of different, I don't know if you know, but it has a lot of different radius reported in the literature. So they are not consistent with one another. So this is probably the reason why we see a deviation. But otherwise, this is first proof of a concept. It's working pretty well. Now I'm going to be talking about HD189. So here are 3 different visits to HD189. This is G141 data, and these are single component fits. And now we use 2 components, which is you assume there is a different component. There might be spots on the surface of the star, and it might have a different temperature. And you assume that spot are stars with lower temperature. So we are still using Phoenix model for them, and we are trying to see if we can improve the fits. So we keep on making our models more complex. So this is a 3-component fit. And now once we have all this multiple component fit, what we do is we look at the Bayesian information criteria and see which one best describes our fit, which gives the best result. And in this case, the second, this 2-component fits is the preferred result. And I think one of the more exciting thing, or maybe something people not have, which is usually not the case in literature, is we usually tend to find very high fraction coverage, which is in this case is around 30 to 40%. But if you look at the test slice curve, right, you see that the photometric modulation for SD189 is around 1%. So how do you reconcile these 2 facts? This can be explained if the SD189 has high asymmetric spot coverage. So that's the way you can explain, and these are the 2 scenarios that is presented from Isaac's paper. And Ben would be actually talking also about TRAPPIST-1, where the inferences is we have very high fraction coverage of the star that's covered with spots, and they are very well mixed. And if you have more questions about this result, this is really great paper, please talk to Ben. His talk is on 9 o'clock on Thursday. So last but not the least, I'm personally working on HATP11, and I'm trying to do similar analysis. The great thing about HATP11 is it has 4 years of Kepler data. And based on this data, because the star is perpendicular almost to the plane of the axis for the planet, we can constrain I mean, there are multiple spot occurrence during the transit, and that sort of gives us, the spot fraction, coverage fraction as around 3%. And the error bars are +6 on the positive side. And we do our analysis, and what we find is we find around 30% coverage, fraction coverage. And the great thing about Hubble data was also that you can see a spot during the G102 transit. And like this is something I'm trying to make sense of it. I don't have a perfect explanation, but the amplitude seems to be going the wrong direction. We sort of expect the amplitude to be increasing with lower wavelength. But I think this is not totally unexpected because there might be features, and it might not be like perfect black body. And another thing, I think this was also kind of exciting because we looked at the Kepler data and we looked at the test data. And the Kepler data, 29.3 days orbital period, we see that. And in test data, you phase fold it to the same orbital period, and we don't see it. And the test data, because this is like very bright target, we are able to, we should be able to see the same modulation, but we don't see. And one of the explanation, I think, is, I'm sorry, I'm running a little bit low on time, but it's because of the stellar activity cycle, which is supposed to be around 10 years. So maybe that might be the reason why we are seeing this. And finally, we do see calcium lines in G102, and between different visits, we can see the lines are changing visibly. So we are also trying to see if they correlate with anything about the stellar activities. This is an ongoing analysis. And with that, I will leave you with my conclusion side. I also have a poster on opacities, and if you want to talk about that, I'd be more than happy to. Thank you.
Questions for Prajwal?
Thank you, very interesting. Did you say that the period of HAT P11 is 29 days?
Yes.
Yeah, so that's very close to the orbital period of TESS, so it will be quite hard, I think, to measure that rotation period with TESS, depending on which light curve extraction and how you get rid of the systematics. But there are other people in this room whose business is to do that, so maybe they can help.
Yeah, no, that's one thing we're considering. Yeah, that might be a challenge, I guess, given it's 29.3 days.
Elizabeth Newton, Dartmouth. I was following on that. I was wondering which test data reduction that was.
I think this is Spock. Yeah.
Is it so the PDC SAP though?
Yes.
Steve Sarr, what models are you using for the spots?
We're considering Phoenix. We're considering the spots are also start at lower temperature.
So basically the same gravity but lower temperature.
Yes.
The problem is that spots are evacuated, so they have much different density than a normal dwarf. So I don't know if a dwarf spectrum is quite appropriate. That might change the analysis.
Yes. No, we are working with stellar experts. Maybe we can improve the stellar models, but for now, I think this is what we're doing.
Hi, Sabina Saginbayeva from Stony Brook. Awesome talk, thank you. I'm curious also about HAT P11. So it has been so the spot evolution of HAT P11 has been very well studied with Kepler. I'm curious if you added something that we haven't seen before with HST data.
Yeah, no, I think one of the things we are trying to analyze is, can we see the temporal variation? And I'm not quite ready to show that figure yet, but we do see, the spot coverage fraction changing between different epochs of HST visit. So hopefully we can tie that with the rotation period, and maybe we can say something more interesting. So this is an independent way of talking about the spot coverage fraction compared to Kepler. So we should have some interesting conclusion to say about HAT P11.
Great, and on that note, let's thank Charles Wall again.